In this lesson, we're going to talk about derivatives of polynomials and exponential functions using differentiation formulas. First, I want to look at different notation for derivatives. We have f prime of x, which is very common. You have y prime, and then right here, this is dy dx. So this is Leibniz's notation for derivative. It's nice because it specifies that you're taking the derivative of the function y with respect to x. Right here you have d dx of f of x, so you'll notice this will be used when you don't have an equation in like a y equals form. It might just be like d dx of sine of x. And then these two, I honestly haven't seen them used as often, but I just wanted to include them here for reference. Again, all of these refer to taking a derivative. For this first example, we're just going to look through some typed out problems. So for the function x cubed, when we take the derivative using the derivative formula, the limit as h goes to 0. This is f of x plus h minus f of x all over h. You can see right here x plus h was plugged into the function. Here's your f of x. And then if we multiplied this out using binomial expansion, you would get this expression right here, and then you can see the minus x cubed drop down. When we get down to here, it says the limit as h goes to 0, so you can see the two terms with h would go to 0, therefore our answer is just 3x squared. So again, the original problem was x cubed, and the derivative is 3x squared. For part B, similarly, we have f of x equals x to the fourth, and we have all the same steps written out here, and I just wanted to focus the original function is x to the fourth, and the derivative using the derivative formula becomes 4x cubed. This last one that I have written out for us, the original function is 3x squared, and when you use the derivative formula, you get 6x. And again, I want to look at all three of these and look for the pattern. Right here, the function was x cubed, and the derivative is 3x squared. Right here, the function is x to the fourth. The derivative is 4x cubed. So you might be noticing the pattern by now. To take the derivative of a monomial, such as these, you take the power and bring it to the front. If there's already a coefficient, you would take the power and multiply it to that coefficient, and then you subtract 1 from the exponent. Okay, so this is super exciting. This means that we are introducing differentiation formulas. So this long process of using the definition of a derivative, we can finally put that past us, and now we can take derivatives using these differentiation formulas. I'm so excited for you guys to be able to do this. So our first differentiation formula is the derivative of a constant function. The derivative of a constant value equals 0. So I want to show that graphically over here. Here we have a constant function, and you can see that if you take the slope of the tangent line at any point along the curve, you get a slope of 0. So you graph that, and you get a height of 0 for f prime for all the values. So here we're showing graphically that the derivative of a constant value is 0. The next one's the power rule. So anytime you have something of the form x to the n, you bring the n and you multiply it to the front. Then you subtract 1 from the exponent, giving you your new exponent. Next, we have the constant multiple rule. If you have the derivative of a constant times a function, you can pull the constant to the front and then take the derivative of the function. Right here we have the sum rule and the difference rule. For the sum rule, if you have a sum of functions, you can take the derivative of the first plus the derivative of the second. And similarly for the difference rule, when you have the derivative of a difference of functions, it's going to be the derivative of the first minus the derivative of the second. For this example, it says use the power rule to find the derivative. This first example says f of x equals x to the 8th. So we're going to write f prime of x, and we're going to bring the power 8 to the front, and then we subtract 1 from the exponent. So our answer is 8x to the 7th. For part B, we have y equals kt to the 5th. For this problem, k is going to be a constant. So when we bring the power 5 to the front, we write 5k, and then we have t to the 4th. So again, the power came to the front. We multiply it with whatever's in front, and then we subtract 1 from the exponent to get 4. For part C, you'll notice that 1 over x is not in the correct form to use the power rule. So we're going to first rewrite this as x to the negative 1. So by doing that, now we have this in the form x to the n. And now we can take the derivative using the power rule. So to take the derivative, we're going to take the exponent of negative 1, multiply it to the front, and then we subtract 1 from the exponent to get a total of negative 2. Last step is you want to rewrite the answer in the format that the problem was originally given to you in. So since the original problem was given in the form as 1 over x, we want to put this back in that kind of a form. So our final answer for the derivative is going to be negative 1 over x squared. For part D, we have f of x equals the square root of x. So again, in order to do this problem, I want to rewrite it so that it's in the form x to the n. So now we have f of x equals x to the 1/2. So f prime of x equals And again, I want to rewrite this so that it matches the format of the original problem. So we're going to move this to the denominator and rewrite it as a square root. So our final answer is 1 over 2 root x. For part E, we have h of x equals x minus 5 times x plus 3. In order to do this problem, we're going to first FOIL, and now we're ready to take the derivative. So when you take the derivative of something with multiple terms, you just take the derivative of each term individually. The derivative of x squared is going to be 2x. Next, the derivative of negative 2x. Technically, the x has a power of 1, so you take the 1 and multiply it to the front, so you still get negative 2. And then you subtract 1 from that exponent, so you'd get 0. So x to the 0 is a value of 1. And then finally, the derivative of this constant is 0. So our final answer is 2x minus 2. For part F, to take the derivative, first we need to rewrite this, so we're going to rewrite it in the form x to the 2/3. So now it's in the right format in order to use the power rule. So we're going to bring the power to the front, and then we're going to subtract 1 in the exponent. So 2/3 take away 1 is the same as 2/3 minus 3/3, which makes negative 1/3. And finally, we want to put this back into the format that matches the original problem. So our final answer is 2 over 3 cube root of x. For this next example, part A, we want to first rewrite negative 3 over x to the 5th into a format where we can use the power rule. I rewrote it as negative 3x to the negative 5, and next, to take the derivative, we're going to multiply the negative 5 to the front number, and then we subtract 1 from the exponent. And last, we just want to rewrite the format so that it matches the original format. So you get 15 over x to the 6th. For part B, we're going to take the derivative of each term individually. The derivative of x to the 8th is 8x to the 7th. The derivative of 2x to the 4th is going to be 8x to the 3rd. The derivative of negative 3x squared is going to be negative 6x. And to take the derivative of negative x, the exponent is a power of 1. So you multiply the 1 to the front, which makes negative 1. And then you subtract 1 from the exponent. So 1 minus 1 is 0, x to the 0 is 1, so you just get negative 1. And last, this is a constant. The derivative of a constant is 0, so you don't need to write anything there. So here's our final answer. For part C, we have y equals the 4th root of x times the quantity x plus 7. So to take the derivative of this, we need to do some manipulating. We want to have our function to be more like this format. So in order to do so, first step, I'm going to rewrite the 4th root of x as x to the 1/4. Next, we're going to take x to the 1/4 and we're going to distribute it to both of these terms. So remember, when you multiply x to the 1/4 times x to the 1, they have the same base number, so when you multiply, you're going to add their exponents. So we have 1/4 plus 1 will be 1 1/4, or you can think of it as 5/4. We're now ready to take the derivative. So I moved the 5/4 to the front, and then I subtracted 1 to get 1/4. For this problem, I dropped the 7 down. So again, that's kind of like the constant multiple rule. You can bring a constant to the front, then you can take the derivative of the function. So the derivative of x to the 1/4, we multiply the 1/4 to the front, and then we subtract 1 from this exponent, which gives you negative 3/4. And finally, I just rewrote it so it looks similar to the format of the original problem. 5 over 4 times the 4th root of x plus 7 over 4, and then I took this x to the negative 3/4 and rewrote it as the 4th root of x cubed. For this problem, we want to rewrite it so it's in a format that we can take its derivative. So first, I just rewrote the square root of x as x to the 1/2. So at this point, I'm going to split these into 3 different fractions: x squared over x to the 1/2, 4x over x to the 1/2, and 3 over x to the 1/2. Remember, when you do x squared over x to the 1/2, you have the same base number, so you can subtract exponents. So we're going to go 2 minus 1/2, and that will simplify to 1 1/2 or 3/2. Next, we have x to the 1 over x to the 1/2. Again, when you subtract 1, take away 1/2 is going to be positive 1/2 in the numerator. And then last, we have 3 over x to the 1/2. So we're going to rewrite that as 3x to the negative 1/2. And now we're ready to take the derivative. So the first term became 3/2 x to the 1/2. The next term, I dropped the 4 down. Again, constant multiple rule, you can drop the 4 down and then take the derivative of x to the 1/2, which is 1/2 x to the negative 1/2. And similarly, for this last term, we drop the 3 down, you bring the negative 1/2 to the front, and then you subtract 1 from the exponent, which becomes negative 3/2. Last step, I'm just going to rewrite this. This time I left all the x's as x to the 1/2, Right here, I simplified the 4 and 2 and got 2, and then just rewrote this as x to the 1/2 in the denominator. And similarly for this last term, I rewrote this as -3 over 2x to the positive 3/2. This next definition says, the normal line to a curve C at a point P is the line through P that is perpendicular to the tangent line at P. So the key word is perpendicular here. For the slope of a tangent line, you're still taking a derivative, but once you find that slope, you can find the line perpendicular to it, which would be opposite reciprocal slopes, and that will give you the slope of the normal line to the curve at that point. This example says, let f of x equal x root x. Find equations of the tangent line and the normal line to the graph of f at the point 1, 1. So before I did anything, I rewrote f as x times x to the 1/2, and then multiplied these together by adding their exponents. So remember, this has a power of 1, so 1 plus 1/2 makes x to the 3/2. So now we can take the derivative of f in order to find the slope of the tangent line. So f prime equals 3 square root of x over 2. And to find the slope of the tangent line at the point 1, 1, we're going to plug in this x value into the derivative to find slope. So the slope of our tangent line is going to be 3/2. And it wants the equation of the tangent line to the curve at 1, 1. So the equation of the tangent line of f at the point 1, 1 is going to be y minus y1 equals slope times the quantity x minus x1. Okay, next to find the equation of the normal line to the graph of f at the point 1, 1, first we need the slope of the normal line. So the slope is going to be the opposite reciprocal because the slope of the normal line is perpendicular to the slope of the tangent line. So the slope of the normal line is going to be -2/3. Therefore, the equation of the normal line of the graph of f at 1, 1 is y minus 1 equals -2/3 times the quantity x minus 1. This example says find the x-coordinates of the points on the graph of f where the tangent line is horizontal. So the key to this problem is tangent line is horizontal. When you have a tangent line that's horizontal, that means the slope is equal to 0. So we're going to find the slope and set it equal to 0 and solve for x. So f prime is 4x cubed minus 12x. And we set it equal to 0 and solve. We have a product equaling 0, so we're going to set both of these equal to 0 and solve. So we get that x equals 0 and plus or minus √3. Next, we're going to look at the number e. Remember, e is irrational. It's approximately equal to 2.718. So we have here, it says e is the number such that the limit as h goes to 0 of e to the h minus 1 over h all equals 1. Geometrically, this means that the slope of the tangent line to the graph of e to the x at 0, 1 is exactly 1. And that leads us to its derivative. The derivative of e to the x is e to the x. So it's the nicest derivative, it's just itself, and we have some notes here. The exponential function e to the x has the unique property that it is its own derivative. The graphical implications, the slope of a tangent line to the graph of e to the x at a point a, f of a is f of a, the y-coordinate of the point. So when taking derivatives that involve e to the x, it's really nice because the derivative of e to the x is just itself. So to take the derivative of this expression, we're going to take the derivative of each individual term. The derivative of e to the x is just e to the x. The derivative of negative x is going to be -1. So that's just our final answer, e to the x minus 1. This problem says y equals -5 e to the x. To take the derivative of this, remember, you can use your constant multiple rule. When you have a constant in front, you can move it down. Then you just take the derivative of the function, and the derivative of e to the x is just itself. So your final answer is just -5 e to the x. For this problem, first step, I want to rewrite square root of x as x to the 1/2. And we're ready to take the derivative. So the derivative of x to the 1/2 is 1/2 x to the -1/2. Right here, we drop the 2 down, and the derivative of e to the x is itself. And last, I just want to rewrite this as 1 over 2 root x plus 2 e to the x. And finally, this last problem, again, 2 e to the x, its derivative is just going to be 2 e to the x because you're dropping the 2 down, and then you take the derivative of the function, which is just e to the x. And your final answer is just 2 e to the x plus 3/2 x to the 1/2. This example says find a point on the graph of f which equals e to the x such that the slope of the tangent line is parallel to the line y equals 2x. So first step, I want to take the derivative of f, and the derivative of f is itself e to the x. Next, I want to look at the line y equals 2x, and for this line, we can see that the slope is 2. Next, we want to note that it says that the tangent line is going to be parallel to this line. So remember, parallel lines have the same slope. So if this represents the slope of the tangent line, and for this equation the slope is 2, that means these expressions are going to be equal to each other because again we have parallel lines. So we set e to the x equal to 2, and now we're going to solve for x. Remember, to solve for x when you have e to the x, you take the natural log of both sides. The natural log of e to the x is just x, because the ln and the e undo each other. So you get that x equals ln of 2. We go back to the problem. It says find a point on the curve f of x equals e to the x. So we have an x value. We're going to plug this in to find the corresponding y value. And when you plug ln of 2 in for x, you get e to the ln of 2. The e and ln, they undo each other, and you're just left with 2. So our point is ln of 2, 2. All right, guys, thanks for watching.